Okay, so what we're doing here is we're standing in the closet of a typical network, a small network. In the back here, you may not be able to see. We've got a series of switches and patch cords, patch panels, etc. And we're looking at actually 3 devices here. First 2 that I'll show you is a piece of software, high-end software. It's a custom version of SNMP called Concord. And over here we have a Fluke device. And this is Fluke's highest-end device known as an OptiView. It's a real-time Armon probe. So back over here, the first step of a testing process is to look over here to connect using the Concord software. And the advantage that we have with the Concord software is that we can see across a LAN and we can see across wide area network links to other offices in other cities, other countries, etc., simply from one port in a network, in a closet on a network. So if I want to monitor for errors, both real-time and historical, all I simply need is any number of IP address ranges, specific IP addresses, and a community string, and I can see any network from at any number of any size. It really doesn't matter, simply from one port. And what we do is we'll poll that network for any number of minutes, depending on the amount of volume and traffic that's running across the network. Obviously, if there's a lot of traffic, we're going to let it pull for a shorter period of time, enough time for us to just gather a certain amount of data. If there's very little utilization on the network or traffic on the network, we'll let it pull for a little bit longer in order for us to gather enough data to measure. Once we measure the traffic, we simply run a report right here from the software, and we look for 2 different things, total bits and the percentage of errors. And what we're looking to do is isolate the specific ports on the device that are kicking out a lot of errors. And we can't always diagnose exactly what the problem is with the software, but sometimes we can. And what we'll do is we'll focus on those particular ports, and then we'll move over to that particular device with the OptiView. And the OptiView gives us a little bit clearer picture of what's happening on each individual port. For example, we're actually plugged into this right now, and we're monitoring one of the 3-com superstacks here in the back. And we're plugged in, and we're looking. We've set it to look at one specific switch. We can look at any switch that happens to be on the network behind us. We've got one selected, and we're looking at each interface, each port across that particular switch, and we're monitoring it real time for errors. And what we see coming up at this point is pretty much just a lot of fragments coming across the network. But what benefit this gives to us as far as testing is it helps us eliminate, potentially, some of the problems that may be associated with the cabling. In other words, this device can look for things like interframe gap problems, runs, things that can tell us more definitively that it may be a NIC card or port problem as opposed to the cabling problem. If we can isolate and eliminate the problem using this Fluke OptiView at this point, that's great. Then we can go and actually test our theory by checking the NIC card or replacing the NIC card or running that channel to a different station that has a good NIC card to see if errors continue to come up. Or switch the port. If we believe the errors are at the port, we can switch the port and see if the errors continue. So there's a way we can logically check for the accuracy of that. If we can't, and we can't a good 50% of the time, we're not able to diagnose it with the OptiView or the Concord, we'll plug in a device called the Big Tangerine, which is actually sitting right behind me, and we'll plug that into to the network. Okay, the Big Tangerine that I have up here running on the software now, the device is actually residing behind me, but the software is run from a laptop or directly from the Big T, has a couple of advantages. First of all, it's a very high-end LAN diagnostics tool, and it measures the entire channel. When I say the entire channel, it measures everything from the switch port through your cabling plant to the active device, NIC card be it, at the other end of the device. Okay? What's important about that is we're measuring the IEEE specs, in other words, the electricals of that signal, what the integrity is of that sine wave. And number 2, we're measuring the EIA-TIA specs. But we're measuring those specs in a little bit different way than a typical contractor may or someone who's using a handheld would typically measure it. The difference is that the Big Tangerine actually measures and looks for impedance, frequency, spikes, and not necessarily averages. Your handheld devices are measuring for averages, so oftentimes we'll follow a contractor up and fail channels because it misses the spec, because they don't have that they don't have that type of visibility across the channel that we can see with the Big T. Ready? Okay, the first thing that we see after we've done a shot with the Big T is to my far, or to your far left, this is actually our interface unit. And at this point we've shot 20, well, we can shoot up to 24 ports with this interface unit. the big T is capable of shooting 96 ports simultaneously. Looks like we've got, approximately 12 cables that we shot off of this particular switch. In other words, we looked at the number of the SNMP from the Concorde and the OptiView, determined which ones we needed to shoot, and plugged into those specific ports. In this case, 2, 5, 6, 7, 8, 10, 12, 13, 21, 22, and 23. So we know that there were potentially some problems on those particular ports. If we look at a little bit closer, they're marked by color. Anything that's in yellow, as in the channel, means that it was marginal and it's beginning to fail the EITI spec. Green means it passes. Red means it failed the EITI spec. The initial red dot is the IEEE spec for the switch port. If it's green, it passed. If it's white, it did not transmit. The big T doesn't use the smart bits. It actually has to measure the signal that the active component would normally use. Same thing for the NIC card. And so if it does not communicate, we can't not measure that IEEE spec. If that's the case, if we really want to look at that channel a little bit more carefully, we can just simply set the device to ping. I can set the device on the far end to ping, and it'll look for a reply, and we can simply measure the spec that way. If I look down a little bit further, and X resides on this very last channel, that means there's outside emissions on the channel, be it from overhead lighting, air conditioning, any number of things could cause that. But we're able to identify that. When we look at the device, the active device on the very end of the channel, they tend to be color-coded as red, yellow, or green. Green means it passes the IEEE spec for the active component on the far end. Yellow means it's failing. And a triangle means that device didn't communicate. So if we really want to look at that device again, we can just simply set it for a continuous ping and hit the button again and run the test again fairly quick. This test right here took about 3.5 minutes probably to process. Okay, so now what we're going to do is we're actually going to drill down into each one of these channels here and look at what the individual problem is. And this is what we call root cause analysis, because we'll be able to pinpoint exactly what spec failed and what we need to do to correct it. Okay, by simply clicking on that particular channel, which is a link, it brings up a summary of the EIETI specs, because we're looking at the channel. And if I scroll down here, it tells me exactly where it failed and on what pair. That pair 2 has an R-loss problem. Okay, and by clicking the signature tab, now I'm actually looking at that particular channel. The first screen that comes up by default is the impedance versus distance. And you'll see there are 4 lines. There are 2 that are yellow and 2 that are red. Your yellow lines are your EITA spec line, okay? The red line is 10% beyond the spec line. This is your impedance, and across the bottom is distance of the channel. And the cursor, as we run it across, will actually measure the distance to each one of those impedance spikes. And why is that important? It's important because a typical handheld tester is measuring averages. It's not looking for the spikes that you see on this particular channel. Every time you have a spike, depending on the severity, there's reflection, there's return loss, and there's potential for errors. In this case, it's just within the spec line, so technically it passes the spec line, and according to the SNMP report, is not necessarily yet the source of the errors. But we're going to drill down a little bit, because what failed here was the return loss. By clicking the second spec, which is impedance versus frequency, what again we see here, the 2 yellow lines, if you can see them in the middle here, represent the EITI spec, and your red lines indicate 10% beyond that. We're able to measure this. Actually, we can measure out to 250 megahertz, but we can see that the channel maintains basic integrity all the way through to about 97, 98 megahertz, which should be enough to guarantee that this channel gets 100 megabit throughput. So we don't see any problems here either on the frequency. The only thing we see at this point is some impedance spikes at the patch cord and punch down, as we saw on the previous screen. Okay, what we're looking at here is actually where it failed the spec, and you can see the green line pretty clearly, I'm hoping here, of which particular pair. It happens to be pair 3 that's falling out of the return loss spec. Now, if you recall the very first screen that we saw, the impedance versus distance, if you recall, and I'm going to switch back to that real quickly, if you recall, that spike that happened to occur not only in the patch cord, but on the punch down was pair 3. So when we went back and we replaced that patch cord and punched down pair 3, it brought the R-loss back into spec. Okay, what's important about knowing, about being able to identify that the punch down was the problem with the channel is that a typical network administrator, if he's got errors on his network, will re-terminate the connection, change the patch cord, replace the NIC, and sometimes this can take hours, days, weeks of analysis to determine where the problem is. This whole analysis probably took us, including setup, about 30 minutes. Okay, we're back to our main screen, and what we're going to do is we're going to come down here and actually look at a channel that clearly failed the EIA-TIA spec, and we're going to click on that, and it's going to quickly tell us that it failed on pair 3 and it failed the frequency spec. Signature of that channel, again, the first thing that comes up is the impedance versus distance. You can clearly see again a spike right in the middle of the patch cord, but again it's within the EIA-TIA specification. But when we drop down to the frequency, we'll notice that the frequency starts coming out of spec clearly 10% beyond the spec, somewhere around 97, 98, which realistically is not very bad. So technically, they should be able to get about 100 megabit of throughput on this particular channel. But it's exceeding the 10%, so therefore it's failing the spec. Okay, now what we're looking at here, we're back to our main screen, and we're going to come down here and we're going to actually look at a switch port that is indicating that it's beginning to fail the IEEE spec. In other words, the integrity of that sine wave, of that signal that it's kicking out, is suspect. And by clicking on that particular port, we're going to start to see some history and some historical data that will help us identify what the problem is with this particular port. And what we see down here under warning is that the fall time is starting to fail on this particular switch port. When we actually step in and look at that particular device, there's not a whole lot of data here. You can only see one green dot. In other words, there's only one sample, one packet that went through for this particular test. We can leave the device active. It doesn't interfere with someone who's working on that particular end station, and we can continue to measure that for any length of time. But that particular rise time initially, the rise time is also right there on the spec line. And then as we drop down and we look at the fall time is actually below the spec line, clearly out of spec. And we can simply go down and look at all the different specs from jitter to amplitude to bottom to edge symmetry, etc., to measure the integrity of that sine wave. The more that it's out of spec and the longer the cable run, the more attenuation, the harder time that that end device is going to have in recognizing that signal, the more problems that you're going to have with any application that you have, especially as we move into more real-time applications like voice over IP or streaming media. Okay, next thing we're going to look at is an end device. In other words, we have over here at the very top a NIC card that is also marginal, beginning to fail the IEEE spec. When we select this particular device, we can scroll down quickly and determine which particular spec failed. It happens to be the amplitude that fails on this particular device. And NIC cards are hard to diagnose. It's very difficult for a network manager to determine that a NIC card is failing an IEEE spec, because Cisco Works, HP OpenView, you know, they're not looking at the integrity of the electrical signal across the wire that device is generating. So they're not capable of seeing those types of errors. Again, we can go down and look at the different amplitudes as they approach the spec line, and we'll be able to clearly see right here it was amplitude to top that is exceeding the spec on this particular device. So again, as the cable run, the longer the cable run, the more attenuation, the greater chance that this particular device is going to have a hard time communicating. Therefore, retransmissions will occur, bringing down your network. So why TrueNet? Why is TrueNet important here? And what I have here, if you'll scroll, pan down here to the screen again, is some shots of a TrueNet installation to give you an idea of what a TrueNet channel looks like and the advantages of TrueNet. What a good TrueNet channel looks like. That's pretty darn good. I've seen better, but that's pretty darn good. Okay, what we've got here is the first impedance versus distance for a TrueNet channel that I shot. And you can see how the parameters are very tight, plus or minus 3 ohms. Very little return loss, very little insertion loss delay, very little impedance on the channel. This channel is easily upgradable to gigabit should the customer want to move to more real-time applications like voice over IP, etc. Because in this case, when you're using quality of service and you're going to tag packets, if you've got a problem anywhere along the channel which is a source of errors, it really doesn't matter what type of quality of service you assign. It could potentially give you a lot of problems with that particular application. With TrueNet, we guarantee a 0-bit error rate, and you can see clearly how tight the channel is, and this is a way that gives us some visibility into the performance of our network. You can see, but it's darn good within spec. Okay, with TrueNet, again, just a summary, this type of service is what's included with any TrueNet installation to guarantee that a network, not just the cable is running bit error free, but that your active components that are working as a tuned system with your cable plan are also running optimally. And if we discover problems with your active components, we produce a document that indicates which active components are bad and need to be replaced now, which ones are marginal that you'll want to monitor, and whether or not there's a problem with your cable, in which case we'll come back out and recertify that cable. So what you end up with as an end package is a 0-bit error network.